Okay, let's do this problem from your homework. I'm actually not going to use equivalent capacitances here, even though we just kind of learned about it, just because I want to show you how like the node voltage analysis process would be paralleled for just capacitor problems. So we're going to do pretty much the exact same thing, except the equation that we're going to use is this Q equals CV instead of V equals IR. And instead of the currents, we're going to write some relationships between the charges. So let's first do our usual labeling. So you're going to have to choose labeling for the capacitors. And I think it makes sense to do it like the way it would actually work in real life. But again, like it doesn't matter really. But basically like you have this like positive charge repelling some positive charge onto that plate. And so like the labeling you'll end up with is that you have some positive charge here. And then that means there's positive charge on each of the top plates. And then on the bottom plates, you can have negative charge. Okay, so we labeled them, and then let's give our capacitors some numbers as well. Letters, sorry. Let's say this is C1, this is C2, C3, and C4. Okay, that should be good enough, and now we just need some nodes. I call this node 1, call it node 2, and node 3. Node 4 is just our ground node. Okay, maybe I will make it bigger. Okay, so the first one we can write is an equation across C1, where we know that above it is positive, so we can do U1 minus U2 is the voltage across that capacitor. And let's see, how do we want to write this? Maybe we can write it as V equals Q over C. Yeah, let's do that. So V is equal to Q, and we're always going to be using the positive charge here. So basically just the magnitude, Q over C. C1 and Q1. Okay, so across C2, we have U2, and then on the other side, you have this ground node that's just connected to ground. So U2 minus 0 is equal to Q2 over C2. Across C3, you have U2 on the top and U3 under it. So that's going to be our expression. And then lastly, for C4, we have U3 minus 0, 0 being the ground node, which is Q4 over C4. Okay, so these are the ones we have, and we actually know a good bit of information about this stuff. So we know that U1, for example, is going to be the voltage of our battery, so that's going to be 10. And we know C1, C2, C3, and C4. So let's just write those. C1 is 3, C2 is 4, C3 is 6, and C4 is 3. Okay, so we know these, but of course this is not enough. You have way too many variables, so you need something relating just the charges as well. So that was kind of paralleled with like us relating the currents. And what we're going to use is what I talked about in the previous lesson about series stuff. I'm going to recap it once more, where any node where only capacitors are connected, for example, this node right here, is going to have the same net charge as it did before being brought into this circuit. And usually that means if these were just uncharged capacitors that you brought into the circuit, which will be typically what you do, where like this kind of existed somewhere else, but there was no net charge on these, that property of no net charge is going to remain. And once again, the reason is that there's nowhere for these charges to go. You cannot travel through this insulator that is air. So you cannot travel through that region because you can only travel through basically a wire, which is a conductor. So yeah, there's nowhere for these charges to go. They can just kind of spread around and polarize. So you can have positive charges move here and negative charges move the other way, but you're not going to lose charge. Okay, so one more caveat is that like sometimes you can have charged capacitors where you have like multi-step problems with like a switch that charges one. Maybe I'll do an example of that. That's basically falls under the category of charge sharing. Anyway, so from here what we can say is that this negative charge plus this positive charge plus this positive charge is going to be 0. So this negative charge, it's going to be negative Q1. And the reason being because Q1, Q2, and Q3, they always represent the magnitude of the charge. But in this case, we actually care about the sign. So negative Q1 plus Q2, that's positive, and Q3. And this is kind of the choice that's dependent on my labeling. So this part, and me finding like the difference in voltage. If I flipped my labeling, I would be subtracting the reverse node than I am currently. So instead of U1 minus U2, I'd be doing U2 minus U1. And then I flip the sign. So that would kind of balance itself out. But yeah, we don't need to really worry about that. I'm just going to do it this way for now. We're going to say this is which implies that Q1 is Q2 and then the other one, is right here, where there's nowhere for the charge to go. Remember, like, anywhere, like, here, the charge can kind of freely move around, because there's this battery here. You could, yeah. So the only ones that are so-called splitting nodes, if I write them down, they still use this terminology, are node 3 and node 2. Okay, so we have this, and at node 2 we have negative Q3 plus Q4 is equal to 0, so Q3 is equal to Q4. Alright, we have both of these. So let's do some plugging in. So let's plug into the Q1 equals Q2 plus Q3. So Q1 is equal to 30 minus 3U2, which I got from this equation right here. And then that's equal to Q2, which is 4U2, plus Q3, which is 6 times U2 minus U3. Alright, so I have two variables here, not too bad. And then Q3 equals Q4. So Q3 is this 6 times U2 minus U3. And that's equal to Q4, which is 3 times U3. So this should be actually pretty straightforward to solve because we only have two node voltages that we're looking for. So let's solve the bottom one first and find an expression for U2 or U3. So we'll say 6U2. Let me do this on the left side. So 6U2 minus 6U3 is equal to 3U3. So 6U2 is equal to 9U3, and U3 is equal to 2/3 of U2. Okay, so we have this expression relating them. We just have to plug into the first one. So let's do that. 30 minus 3U2 is equal to 4U2 plus 6 times U2 minus 2/3 U2 instead of the U3. So this just becomes 1/3 U2, and this becomes 4U2 plus 2U2 plus 3U2 is equal to 30. And 9U2 is equal to 30. So then we have an expression for U2, which is 30 over 9, or 10/3. Remember, this is potential, so that's in volts. Alright, we can also find U3, and we already know U1, because that's just the battery. So U3 is just going to be 2/3 of this, so 20 over 9 volts. Okay, so I didn't really describe the question, but this question, it's just from your homework 7, I believe. It's one of the practice ones. What it was asking was basically the voltage across each capacitor, and we can just compute that real quick. So across C1, we know that the voltage is U1 minus U2. Across C2, it's just U2. Across C3, it's U2 minus U3. If you're not seeing how I'm getting that, I'm just taking the node above, which in this case is U2, and then subtracting the node below, which is U3. And I'm doing above minus below because my above is a positive one. So that doesn't necessarily have to be the case. Okay. So like we had said, VC1 is equal to U1 minus U2. VC2 is just equal to U2, VC3 is equal to U2 minus U3, and VC4 is equal to U3. All right, so we just need to compute two of these. U1 is 10, U2 is 10 thirds, and then here it's just 10 thirds. This is 10 thirds minus 20 ninths, which is 30 ninths minus 20 ninths, which is 10 ninths. U3 is 20 ninths. And let's compute this last one, which is 30 minus 10, which is 20 over 3. All right? Yeah, those are our four voltages across the capacitors. You can probably double check with those with the homework. I believe they are correct. Yep. Thank you.